Today we're going to look at, as we mentioned, the elastic interaction between Mauna Loa and Kilauea. And this is published November 18th, 2022, so just last week. It's open access on Nature. And this is by Monica Prozior and others, a group out of Spain and Italy. And I won't go through all of this, but one important part of this, which is a big part of the paper I'm not talking about as much, is this independent component analysis. So they're actually using INSAR and GPS data and doing a lot of this similar kind of modeling as we've seen in the past. But they're using this independent component analysis, ICA, to try to untangle the two different sources, the Mauna Loa source and the Kilauea source. And it seems like they do that pretty well with this mathematical tool, essentially. So they spend time talking about that process of how that's done. But the bottom line is they're also integrating their GPS stations, which are shown up here in the upper plot, with the INSAR scans that ideally are capturing the summits of both volcanoes, so they can use one single scan and look at the differences in Mauna Loa and angle capture there. And they do that over time, and you can then produce a model of so here is that combined INSAR on the left, and then they try to break it into different components, ICA 1 and 2. So this is a Kilauea dominant, and that's the Mauna Loa dominant with very little of the other. So this is basically just a support for the process working. And ultimately, they put together a model, and this is the long and short of what I want to talk about with this paper, is summarized by this graph. So a couple interesting things here. Let me zoom into these by panel. So they have a DM of Hawaii Island, this cross-section going across it here. So across both Mauna Loa and Kilauea Summit. Mauna Loa and Kilauea Summit, this is exaggerated, of course. And as is the size of these features in here. But Mauna Loa essentially has one big reservoir that's largely one big blade. It doesn't have these multiple reservoirs that Kilauea expresses, having a more spherical, shallower magma reservoir, and then having this deeper one that, through their analysis, actually turned out to be more of a sill, more like of a flat blade, rather than being a large spherical body. Right, so that's another interesting result that we'll have to see how that plays out in research in years to come. But this is the ultimate reason why they come to the results. So they actually can model. For example, down here, this is what happens if this deep blade of Kilauea has extra pressure, right? And so that actually creates additional stress in the two ends of that blade, but it doesn't really come all the way over to Mauna Loa. Mauna Loa is all the way over here. So you see that's very localized effect of Kilauea, and it's kind of not strong enough to get all the way across there. If you see, this is Kilauea. Kilauea's shallow chamber. So if Kilauea's shallow chamber is inflating, then it's putting pressure in a larger area around Kilauea, but it's also still not reaching over to Mauna Loa over here. In contrast, this is what happens if you inflate Mauna Loa. Because of the shape of that reservoir in there, it seems like you actually get a fairly decent stress transfer. It actually comes into the shallower Kilauea reservoir. So one of the key results that they find here is that in this analysis, which actually I should have stated earlier, spans from 2003 to 2010, they see that inflation in Mauna Loa can actually override and stop inflation in a shallow part of Kilauea, but not in a deep part. So deep part not affected. It's shallow Mauna Loa, too shallow Kilauea, one direction, but shallow Kilauea does not affect Mauna Loa. A one-way process there. So as Dane said at one point, Mauna Loa, once she decides to bully Kilauea, she just steps in and just takes over by this kind of process. So, but to put it in perspective, we have talked about this 10-year-old paper in the past by Gonerman and others, coupling Mauna Loa and Kilauea by stress transfer in an asthenospheric melt layer. This just means that layer down in the mantle, way deep down by the hot spot. Just think of it that way. So to recap, there is these two pathways into Kilauea, Mauna Loa, and they're fed from the hotspot, and the hotspot has this kind of layer that's common to both feeder sources there, and depending on the pressure that's able to come out of one of these feeders, then it can essentially reduce pressure all the way back down the feeder source, which can then affect pressure at the neighboring pathway up. So if Mauna Loa is pulling more pressure, then it might reduce the input into Kilauea potentially. That's something that's a slower long-term process. We've seen the modeling results that indicated that you have something like a 6-month delay or so between one of the volcanoes doing something and having that effect visible in the other.